Good morning, everyone. Thank you for having me here. I'm excited to give this presentation. It's become a little bit of an annual event, and it's a nice group to talk to. If there are questions, please feel free to jump in the middle. I'm going to try and go through the construction process of an offshore wind farm, so I may defer your questions, but like I said, please feel free to throw them out. And my presentation is going to be on infrastructure requirements for Carolina's offshore wind industry. So I'm going to talk a little bit about introductions. Who am I? Who is COWI, and why am I qualified to talk to you? Catherine did a great job of queuing me up for the status of offshore wind in the U.S. and in the Carolinas. And then we're going to go through the different phases of building an offshore wind project. And this has been more or less arranged and reorganized this year to follow the different types of procurement packages that some of the developers might use. We're going to briefly touch on the two case studies of U.S. demonstration projects, and then have time for questions and answer. So who am I? I'm Brent Cooper. I'm a professional engineer licensed in South Carolina. I have been working in offshore wind for about 12 years now, primarily on the offshore foundation side, as well as the port infrastructure from which the construction projects are launched. Okay, and I work for a company called COWI. I like to introduce the company as the biggest company no one's ever heard of, but we're about 7,000 employees worldwide. We're only about 300 in North America, but our focus here in the U.S. is dedicated to heavy infrastructure projects, so primarily bridge, tunnel, marine projects, and energy projects. We really focus on the offshore energy space. So we have about almost 30 years of offshore wind history at this point, beginning with the Vindeby project in Denmark in 1991. At this point, we're the designer responsible for over 550 turbines. The foundations that are actually installed in the water, supporting about 1,800 megawatts. And we have ongoing designs for an additional 850 turbine foundations that'll support about 4,000 megawatts. We have a full range of consultancy and engineering services from site identification up through design and construction supervision. So our purpose here today, we want to talk about what have we learned in Europe, and how do we make this not a European industry, but how do we apply those experiences and actually build offshore wind in the U.S. And bring it to function in this market. So Catherine covered this. I'm gonna just fly through here. But the Southeast has 5 of the 6 largest electricity markets. Really looking from Virginia southward. We also, due to in many parts being a right-to-work state, but also have a lower labor cost. So our construction costs tend to be lower than the Northeast as well. And Catherine showed this slide, but this just goes to prove that the offshore wind energy resource is more than powerful enough to power over 100% of our current electricity demand. All right, so this slide, we start looking at offshore wind status in the U.S. Right now, and my figure is just a little bit out of date because this was published at the end of 2019. But as Catherine said, there's about 20 gigawatts of offshore wind commitment from the various states, primarily driven by the Northeast. In addition to that, there's about an additional 10 gigawatts or 30 gigawatts total for procurement, but that last 10 gigawatts is a voluntary goal, not a hard commitment. And that's going to the 20 megawatts is going to be about a $68 to $70 billion capital investment. Here we see the different range of projects. We can see all of the kind of the Northeast projects where everything started. Working our way down the coast, the New York, the Mid-Atlantic, and then in the proposed southern areas. So again, status of wind in North Carolina. Like I said, Catherine kind of covered a lot of this, but there are the 3 different areas. The Avangrid project is under development. They are moving along, and they're underway in many of their preliminary engineering studies right now. and the southern areas, Wilmington East and West, are likely to be combined with some of the Grand Strand call areas. So that's likely to be an interstate cooperation between North and South Carolina. There are a couple developers that have expressed interest in the BOEM request for interest in nominations phase, but those lease areas have not been out for competitive auction yet. All right, and so now we're going to get really into the meat of the presentation here. So what's required to actually build an offshore wind farm? Well, first of all, to spend $70 billion, there is an enormous amount of planning, engineering, design, consultancy services that need to go into that planning process. So we really begin with site identification and characterization. So there are companies that will go out and characterize the meteorological conditions, the wind resource, oceanic conditions, what are the wave heights, what are the current conditions, what are the hurricane conditions that projects need to survive through, and then how do we tune the turbines for that. We have to look at existing uses. So there's a lot of competitive uses in the ocean. You go out there, it seems like a great big open space, but there's lots of fishing that goes on. There's lots of oceanic freight commerce. There's cruise ships. There's interstate barge traffic, all that passes through the coast, and these are all existing competitive uses. So we go through a site identification process to find where we have the least conflicts. Once we've characterized the site and identified that, we start looking at the integrated design of the turbine. And this is a really challenging process because most of the turbine design is actually driven by fatigue life. So I have colleagues that like to explain this as we're not so much designing a foundation and a tower as we are designing a tuning fork to operate at a certain set of frequencies while being impacted by all of these different loads. And if we miss that frequency, if it's too high or too low, it can cause extreme fatigue and failure, whether it be in the blades or the towers or the gears in the turbines themselves. There's a huge amount of environmental work that goes into characterizing the site. Marine mammals, right whales are absolutely critical. They're endangered species, and the passage of right whales through an area can really control the construction process. Shipping is only allowed to proceed at certain speeds, up to 10 knots, during times of the year when right whales are likely to be in the area. We have to look out for other marine mammals like dolphins, sea turtles, sharks, etc. So we need to understand where these animals are so that we're not harming them in the process. Catherine started to talk a little bit about the permitting process. In the offshore space, once we're beyond 3 nautical miles from the high tide line, that permitting is done by the Bureau of Offshore Energy Management, and that is a division of the U.S. Department of the Interior, and they lead a multi-step permitting process after the leasing. So they begin with a sampling and analysis plan. The developer, after they're awarded a site, has to submit all of their plans for how they intend to get the detailed characterization information. Once that's collected, that forms their construction and operations plan. And so they then submit all of the designs and their plans for operations. So it's spill compliance, lighting compliance, both for vessel navigation as well as FAA lights. How are they going to mitigate any potential impacts to the military, et cetera, et cetera. Just to give you an example of the scope of that document, the Vineyard Wind Project in Massachusetts, their construction and operations plan is about 6,000 pages of text. Moving on from there, somebody has to buy the power. It's different in different areas of the country, but here in the Southeast, we tend to be more vertically integrated. But either way, the developer needs to come up with a power purchase agreement. And so there's a large amount of negotiation of what is that rate, who's paying it, how does it escalate, et cetera. Those rates then need to be approved by the State's Public Service Commission. And then financing is a big issue, especially for a lot of the smaller private developers that can't self-finance, so they are looking for investing partners. And there's a huge amount of due diligence and then what's called a certification and verification agent. And so CVA is a third-party engineer who comes in certifies that everything has been designed properly, up to sufficient codes, and that an investor's money is going to be well spent and protected. So the nice thing about this is, while we don't have a ton of offshore wind specific experience here in the Carolinas, all of these services and all of these consultancies exist, and so they can be repurposed from other energy or other development industries pretty readily to service the offshore wind market. So after the planning, I'm going to thank Catherine and her group again for this slide. We begin into manufacturing and fabrication, so we need to start building all these pieces. Southeastern Wind Coalition has put together a supply chain map, and in this particular snapshot, which is also about a year old, we have about 275 or so companies that either already supply components to the renewable energy industry or could readily convert. So this could be anything from lubricant for the turbines to fiberglass to the resin, the polymers, gears, cables. There's a huge amount of components that go into these projects. And so then what are some of the specific components? Well, now we're going to look at the different types of procurements. Developers typically will build their projects and contract the construction through a number of different EPCIs. That's a European term. Most of us are probably more familiar with EPC, but the terminology here is engineering, procurement, construction, and installation. So in this case, the construction is really the fabrication. So we begin with the offshore foundations. We need some place to put these turbines. There's really three primary foundation types, beginning from left to right. We look at the gravity-based foundation. So these are generally large concrete structures that are placed on top of a prepared seabed directly onto the ocean floor, and they hold their position due to self-weight alone. We'll look at a couple examples. The next is the jacket foundation. This is what we most commonly see in the bottom-fixed oil and gas industry in the Gulf of Mexico. So lattice-type steel structures. This could be anywhere 36 to 48-inch steel piles, braces slightly smaller, and then maybe 5 to 6 foot diameter piles that's actually embedded into the ground. Then moving on to monopiles. Monopile really dominates the existing global offshore wind industry right now due to its simplicity. And I say simplicity because it's one operation to install one pile offshore, but these particular piles can be, the latest generation, are up to 20 feet in diameter, 6-inch wall thickness, and can weigh almost 1,000 tons. On top of the monopile is a transition piece, and then the tower is bolted on top. We also need these foundations not just for the turbines, but also the offshore substations, whether they be transformer stations, converter stations, et cetera, before that power is transformed and sent to shore. And so I'm going to go through a couple different specific foundation examples and how these are built. So these are the gravity-based foundations for the Thornton Bank project. This project was in about 130 foot of water depth offshore of Belgium. It was 6 foundations of 5 megawatts each, so opposite of the Block Island project. Each of these foundations weighs about 3,000 tons, but is using readily available commercial concrete technology that we're used to day in and day out in our construction. So you can see in the photos here, we've got lots of heavily reinforced cast-in-place concrete traditional rebar. And I like to say that, you know, this is also something we're doing in the Carolinas right now. This is a couple examples from here in Charleston. It's the construction of the Ravenel Bridge over the Cooper River. Same type of concrete technology. And the picture on the right is actually the Clemson wind turbine drivetrain test facility, 15 megawatt testing bed. So this is the reinforcement frame that the dynamometer sits on for that testing. So all this concrete technology is things we're doing right now. I have a couple quick GBF installation examples. So kind of the generation 1 is on the top here. So Gen 1 foundations would have been built totally onshore, and then lifted by a very, very large crane. In this case, the Rambiz is a shear leg crane, has almost 5,000 ton capacity. So self-propelled modular trailers move the foundations to the quayside, cranes lift up the foundations and actually carry them to the offshore site. Generation 2, there's not too many projects that went like this because we skipped relatively quickly through here. This is a semi-floating type of foundation. These foundations displace so much water that they're somewhat buoyant on their own. So the idea is that they are supported by pontoons or barges to provide the extra little bit of flotation that they need to get out to site. But either way, that way you're not paying for the day rate on those cranes. And the Generation 3 GBF, this is kind of state-of-the-art concrete gravity-based technology. This is the Blythe project, which was built by EDF in France. This is actually a fully floating hybrid foundation. So the bottom of the foundation is concrete. The top is steel to reduce the masthead weight, but it's actually fully buoyant and fully stable. So it's built on shore, placed into the water, and then is actually just towed with offshore service vessels or large tugboats. It doesn't require any craneage capacity for the foundation. Next foundation type is looking at steel jackets. So this is an example of the Vickinger project. It's a COWI design in Germany. But this is a very common technology down in the Gulf. We have a number of fabricators who do this type of work. The difference when we talk about the wind industry is that in the oil and gas industry, we're really interested in one large foundation, specifically designed for one installation. Whereas in the offshore wind industry, we really need serial production. We might be talking about 50 or 100 turbines in a project. So the focus now is not how do we build one of these, but how do we build many of them very quickly. So there's a lot of investment going on in automated and robotic welding procedures so that we can move forward more quickly. And as I said, the third most prevalent type is, or the most prevalent type of foundation is the steel monopile. So this is some screenshots from EEW's facility in Germany. They're kind of the state of the art right now of who can roll the largest monopiles. Just to give you a sense of scale, you can see there's a person standing in that center picture on the bottom. So these are, even though they're monopiles, they're really very, very large. The U.S. currently does not really have any ability to produce monopiles at scale. There are some investors and European fabricators looking at partnering with domestic steel fabricators to invest in a facility that can do this. So there's some speculation that this may be coming to the U.S., but we can't currently do this in any kind of mass production. And so this is the top of the monopile. These are the transition pieces. So it's another section of pile, but this is a much more complicated piece. This piece slides on top of the monopile after it's installed. They are grouted or bolted into place. And this houses all of the service vessel landings, corrosion protection. There's a transformer in the base of each of these. There's often survival equipment if a technician gets trapped at sea unexpectedly in a storm. So these pieces actually become very complex. And there's a lot of U.S. fabricators that are really interested in this type of work because our skill set suits this complicated fabrication very, very well. So after the foundations are installed, the next step is that the electrical cables are pulled into place. So the cables that string between the turbines are called inter-array cables. Historically, they've been 33 kV. Kind of the newest turbines are becoming so large, the 33 kV cables are no longer efficient. So the industry is really moving on to 66 or 67 kV inter-array cables. Kind of the interesting thing to note, two of the largest cable manufacturers are Nexans and Prysmian, who both have facilities in the Carolinas. The top picture here is actually Nexan's facility in Bushy Park, which is, let's say about 10 miles from where we were supposed to be getting together today. Right now they have not built a dock, but this cable facility was built on the water side so the cable could be directly loaded into the carousel on the installation vessel. And so we'll see an image of that in the next slide. As projects get further and further offshore, there's a large amount of losses associated with the buried HVAC cables. After that voltage is stepped up, typical export voltage has been kind of 230 kV. A lot of projects are now looking more at 345 kV for a little bit of additional efficiency. But even that, there's too much loss, too much heat loss with the cables buried. So a lot of the new projects are looking at HVDC lines. And those converter stations, just for a point of magnitude, the recent converter stations built in Germany were $1 billion a piece, with a B. We do have a number of the manufacturers who build this type of electrical equipment, whether it's the GE or Siemens or ABB, now Hitachi. These companies all have manufacturing facilities in the Carolinas. So here's a couple slides of the installation examples for the electrical systems. On the top, this is an export cable laying vessel. So these are full dynamic position vessels. They have thrusters on all corners, and the vessels can hold their position within about 3 to 5 feet, depending on the sea state. The cable is unspooled from the reel as the vessel proceeds to shore, and then is buried by a trencher. The bottom left is a transformer platform from a project in the UK. And the right side is one of those $1 billion converter stations from Germany. It's a Siemens design. So Catherine set us up really well here, talking about the turbine size. I like to show this, for example. Up until about 2006, 2007, well, let's step back. The typical turbine onshore is a 1.5 megawatt GE. They really dominate the market with up to about 2 or 3 years ago, almost 70% market share for projects in the US. That turbine size has gotten a little bit larger. They've been able to squeeze a little bit more power out of it to 2 to 2.5 megawatts. But for example, that turbine weighs about 90 tons, being the turbine and the blades. So that's your rotor head mass. That's the 466-foot turbine here. Tallest onshore turbine, that's about those 2.5 megawatt turbines, about 574 feet. Up until about 2013, 2014, the offshore wind industry was really maxed out around 6 megawatts. So for example, the Siemens 6.0 megawatt, 154 meter rotor diameter, that would have been about 750 foot tall. And that had a tower head mass of about 400 tons. The picture on the right is the new GE Haliade X turbine, the 12 megawatt turbine. And you can see, I'm not sure how well it comes across in the presentation, but that's the crew of people who manufactured the turbine. So you can see this is really quite a large machine. This turbine, the turbine itself without the blades, is about 600 tons. And so you're talking about lifting that almost 600 feet high. It's really quite an impressive lift. So what installs all of this equipment and these components? There's a huge amount of vessel spread, different vessels that are required to go out and get this work done. The center or the top two pictures here are survey vessels. So I said there's a huge amount of site characterization going on. They need to go out and characterize the seafloor sediments. There's lots of borings, sediment samples, etc. The top right vessel is actually a marine mammal survey boat. So there's actually, they're surveying for marine life continually during installation. There's foundation transport and installation vessels. I'll show a picture of some of the monopile vessels on the next page. Turbine transport and installation vessels. So what do the vessels look like that can actually lift 600 tons, 650, 700 feet in the air? Inner array cables. So we saw an export cable vessel on the previous slide. This is an inner array cable barge. So this barge was converted to being dynamically positioned. And you can see the cable rail right in the center of the vessel. There's crew vessels that go out, bring the crew in and out, crew changes. Projects that are close to shore, they'll run in and out every day. the projects, as they get further from shore, we're starting to see hotel-style accommodation vessels that may take approximately up to 300 crew, and they'll stay offshore for 14 days at a time. So this is a couple examples of installation vessels. When we started, this is the top left picture. It's kind of circa, let's say, 2008, 2010 GOC vessel. That particular installation vessel is a barge. It's not self-powered, but it is self-elevating, and that has a crane, let's say 800 tons. And then the turbine, or the vessel on the top right, that's actually in process of installing the Block Island Wind Farm. That's a Fred Olson wind carrier Brave Tern, and so that's about a 1,200 ton crane. And the newest generation vessels, we're looking at almost a 2,000 ton crane to be able to lift those turbines. So what we're really interested in here is stability. All of these vessels jack up out of the water. The turbine manufacturers do not let floating vessels lift their equipment. It's just too fragile. So they are required to be more stable at sea. We talked about the load capacity. And like I said, these are massive, massive cranes to get up to rotor height of around 600 feet. Speed, these are not very fast vessels due to their other requirements, but state of the art is about 12 to 13 knots when loaded. One thing that really challenges us here in the United States is the Jones Act, or the Merchant Marine Act of 1920. So this particular act restricts carriage of goods or passengers between U.S. ports to vessels that are U.S. built, U.S. flagged, U.S. operated, and owned. And this was really intended to protect the U.S. in times of war, to make sure that we have a robust maritime industry, both for logistics of moving things around, as well as a robust shipbuilding industry could build the vessels readily. There is precedent from the oil and gas industry that once a piece of foundation, whether it be steel, concrete, whatever it may be, as soon as it touches the ground on the outer continental shelf, legal precedent suggests that it is a U.S. port. So therefore, all of those vessels carrying anything must be U.S. flagged. So this is a couple examples of vessels that we have in the U.S. right now. The top center is the lift boat Robert. This is a traditional three-legged oil and gas type of service vessel. And that's actually at work installing the legs on the Block Island Wind Farm project. As you can see, it's smaller. It has about a 400-ton crane. And then after the piles were installed, to get around the Jones Act, it was actually used to carry the turbine pieces from Rhode Island out to the site. So therefore, the foreign flag vessel that actually lifted the turbines didn't actually carry any of the goods. It was used only as a piece of equipment. The picture on the bottom left is Charleston Heavy Lift's Ocean Ranger. And apologize that no one can come visit our city, but normally you can look out over the harbor and see this vessel and some of its impressive lifting operations. It has about a 500-ton shear leg crane. It is ABS classed, so it can go offshore, potentially for foundation installation, but because it's floating, it can't do any of the turbine installation. And then the picture in the bottom center and the rendering on the right are both the Weeks Marines RD McDonald. So it's an 8-leg jackup. This was actually built, the hull was built in Jacksonville, Florida, and it was taken up to New Jersey for outfitting. This vessel is about half built and has been kind of sitting there waiting for its actual contract. So Weeks Marine has positioned it to be able to complete it quickly, but it's not done yet. Some of the other big news out of the beginning part of this year, Dominion actually announced that they are a significant investor in a consortium to build one of the first Jones Act compliant U.S. specific offshore wind installation vessels. So that's really big news, and we're very excited to have that. So we talked a little bit about the Jones Act. Like I said, Dominion is really going to be the first one that has a compliant vessel that's able to carry the components from port and install them all by itself using a kind of traditional European model. But a lot of the projects that are moving forward are going to use European vessels with feeder vessels that are actually transporting the components. So this is a rendering of some of the class vessels designed by MSC Gusto. They have a facility down in the Houston, Texas area, and are selling their licensing and selling this design to hopefully a few more U.S. offshore wind vessel operators. So now that we have all these vessels, where are they going? As Catherine said, all of these components are very large and heavy. We talked about the turbines are now almost 600 tons. Steel foundations can be 1,000 tons. Concrete gravity-based foundations can be 3,000 tons. So everything really has to be built on the waterfront. The good news is the Southeast and the Carolinas and Virginia have a very competitive port system. We have great ports that are close to the ocean, so good access for the vessels. The other thing that's particularly interesting when we talk about needs of the facilities, our southeastern ports have a lot of staging area. Our ports tend to be bigger than a lot of the ports in the Northeast. We are not as mature as the European offshore wind industry, so we don't have quite as much area. The vessels, when they come in, those turbine installation vessels can charter for up to $350,000 per day. So a project developer is going to want dedicated wharf frontage and exclusive access for that vessel. Given those day rates, they really can't tolerate any loss for another vessel being in the berth. As far as live load capacity, an offshore wind port really is pretty different than a lot of the typical things that we see. Most container ports, container vessels come in and out of, they're built anywhere from 800 to 1,000 pounds per square foot type of live loading. Most of the wind developers and contractors are requesting a minimum of 5,000 to 6,000 pounds per square foot, so 5 to 6 times the capacity. And some in Europe are even being built now with 10,000 PSF within specific crane pads. So they're quite a bit stronger than our current facilities. Some are being adapted, some are being retrofitted, but the majority of ports for offshore wind specific uses are either going to be reconstruction or new build. Navigable depth, that's another great thing here. Offshore wind doesn't require a huge amount of depth. Because these vessels self-elevate, they try to keep them as light as possible. So the installation vessels really only draw about 25 to 27 feet of water, which in context of the container ports that draw 50 to 52 feet of water for in the latest best practice kind of port depth is not a big deal. The real benefit of our southeastern, especially our Carolina ports, are the air draft. Many of the ports in the Northeast are blocked by bridges or overhead power cables, or even glide slopes into runways. They're really limited around 215 feet or so is kind of state of the art in the Northeast. But the Port of Virginia, Port of Wilmington, Morehead City, and Port of Charleston, especially in the Columbus Street Terminal, all of those are wide open, so they have unlimited air draft. I had a client for a particular port authority in the New York, New Jersey area, and they asked me, they said, okay, well, we just raised one of our bridges from 180 to 215 feet. It's no big deal. How much do you need? Well, considering the hub height of the towers, and the tower sections typically come out whole, these vessels really need 400 to 500 feet. So that's of vertical clearance. So that's almost an order of magnitude larger than we're seeing. So the unlimited air draft that we have here in the Northeast is very, very valuable. And then we talked about proximity to the project. And this is just a couple of renderings of two different facilities, both in New York that are moving forward towards being developed. One in Staten Island and one in Brooklyn, what they might look like with offshore wind vessels there. So beyond the manufacturing, the fabrication, and then the construction staging, we're also going to need operations and maintenance ports, and this is going to be a lot easier demand to satisfy. This is a concept from the North Strand Coastal Wind Team. So this is a concept of the city of North Myrtle Beach and some of the places they imagine having service vessels come out of. So service vessels for the day trips, this is kind of a 65 to 80 foot type vessel. They hold 12 to 14 technicians, 2 crew. Here, I'm gonna flip back, but this is the one that was built for the Block Island Wind Farm. So they're catamarans, and they can proceed about 20 to 25 knots. So they're pretty quick vessels getting in and out. Other needs for the O&M ports are obviously we need a place to put the vessel when it gets in. We do need office space. There's accommodation space for the technicians. So because of the schedules, they often need dormitory facilities for technicians to sleep on site. And then an amount of space for warehousing and spare parts. Because this question came up earlier, the typical service kind of interval, the turbines generally have their gear oil replaced once to twice a year. The newer turbines are trending down to 1 time per year to reduce that amount of maintenance. But it's a good amount of oil, and when you multiply by having, it could be a 2 to 3 day operation, you multiply by having 100 to 200 turbines on a farm, you do end up with a year-round O&M program. So one of the interesting things to note is actually kind of the personnel aspect. As I said, some of these vessels, the smaller vessels can go 20 to 25 knots. But if your project is 20 miles offshore and you've got no wake zone, loading time to check in, gear up, you've got an hour plus steaming out to site, an hour plus coming back, and the transfers at the site, all of a sudden looking at a typical technicians, you try to keep them to an 8-hour workday is really totally unrealistic. But a 10 or 12-hour workday, all of a sudden you're losing a third of the day, in some cases more, to that transfer operation. So you're really losing your productive time and losing a lot of time on your personnel costs. So this is a picture of a vessel that was just commissioned by Equinor for one of their projects in, I believe this is Norway. But this type of hotel vessel, this sleeps 150 people. And this is one of the vessels that stays offshore for 2 weeks at a time. And you can see here, this is also a walk-to-work platform. So these vessels are dynamically positioned. They stay in place on their own due to the thrusters. And these are heave-compensated personnel gangways. So there's no more climbing ladders. The fall protection is significantly minimized. Technicians are simply able to walk from the vessel onto the turbine. So just going to look at some of the infrastructure for the U.S.'s 2 first wind projects. So Block Island Wind Farm was the first one. This is Block Island, offshore of Rhode Island, Massachusetts, Connecticut area. It is 5 turbines, some 6 megawatts, and this was an investment of about $290 million. It really worked out well for the developer. It was Deepwater Wind. My presentation is old here. Deepwater has since been bought by Ørsted, so it's part of the Ørsted group. And that project, even though it was very, very expensive, it made sense because all of Block Island was using diesel generator for their electricity. And so their existing rate, they were paying about 27 cents per kilowatt hour for power on the island. And so they were able to, even though the wind project was expensive, they were able to bring the cost down for the existing ratepayers, even on that demonstration project level. Foundations were installed in 2015, turbines and towers in 2016, and the project went online the end of 2016. These are some of the steel jackets that were built in the Gulf of Mexico by Gulf Island Marine. Again, the lift boat Robert from the Gulf, and then the Brave Tern that actually installed the turbines. So some of the portside infrastructure. There was a number of improvements to Quonset Point facility. Some parts of that wharf were strengthened for the crane loading. That was used to compile all the materials before going offshore, as well as the The O&M vessel that was built by Blount Boats, so it's a local Rhode Island boat manufacturer. And the Coastal Virginia Offshore Wind Project is America's first offshore wind farm in federal waters. Foundations and turbines were just installed between May and really the beginning of July this year. Commissioning is anticipated towards the end of this year, with the idea of learning from that project and beginning construction on the commercial scale project to be 24 to 2,600 megawatts in 2024. So in this case, yep, here we go. So here's another image of the project. In this case, to get around the Jones Act restrictions, Dominion hired Ørsted, the developer, to be their EPCI contractor. And then they went to a company called Yondenul, who came in and actually installed the project. But to get around the Jones Act restrictions, they actually staged the project in Halifax, Nova Scotia. So all the projects were compiled up in Canada, then loaded onto Yondenul's installation vessel. And so for each time that I think the vessel had to make 3 trips from Halifax down to Virginia. So you can see that kind of steaming distance is really, really inefficient when you have such a great facility in the Virginia Ports Authority. However, this is coming with investments in Portsmouth Marine Terminal. It's one of the Virginia Ports facilities, and they've got investments from Siemens already for an O&M center. Catherine mentioned the blade manufacturing, looking at some local vessel production, and there's some options to lease. I think it's either up to 40 or 80 additional acres from the facility that choose to be here to expand. And that is my presentation, and I'm happy to take questions.
Brent, this is Cynthia Klein with Duke. This is really, really interesting, and I'm kind of just personally a huge fan of offshore wind. So I have tons of questions for you.
Sure.
Just because this is such a fascinating, I'm so glad David gives us these opportunities. So thinking in terms of North Carolina and South Carolina, what is the overall offshore wind capacity that you see for North Carolina and South Carolina?
The capacity here is really, let me go back to my slides, let's see where we're at. Like I said, I'm a foundations and ports person, so I don't deal on the capacity side as much. You got me on numbers that I don't know, but so I don't speak out of turn. Catherine, if you're still online, you're welcome to jump in on the actual numbers. And we're almost there. Here we go. Oh, missed it. So here's the capacity slides. And these are actually from the Southeastern Wind Coalition.
Oh, perfect.
But just huge amounts of capacity.
On the southeast. Okay.
Yeah.
Oh, awesome. Cool.
And then a lot of the, as Catherine mentioned too, a lot of the capacity factors that we're seeing for the offshore projects, some of the Vineyard Wind, Atlantic Shores numbers, they are really, they're anticipating over 50% capacity factor.
That's awesome. So you mentioned some of the cost of these projects. Block Island was $290 million.
That's correct. The vast majority of offshore wind projects is in the capital expenditures. The O&M is obviously a cost associated with the O&M, the vessels, the technicians to get out there, but the bulk of the cost is in the capital expenditures. So kind of the up until about let's say maybe 2014, 15, conventional wisdom was $3 to $5 million per megawatt installed. We're also seeing that number come down quite a bit with the larger turbines because the amount of offshore time, the vessel day rates are staying relatively similar. They're becoming more efficient, so the vessels are spending less time offshore, and they're needing to install fewer turbines. So we're seeing improvements on that number. Now kind of 3 million per megawatt installed is kind of an upper bound.
And hopefully it'll keep coming down like solar has.
Yes, they one of the projects in Germany last year. I apologize, I forget the name of the project. Had a straight cost unsubsidized of about 5.5 cents per kilowatt hour.
5.5 cents per kilowatt hour.
So it's coming down. Germany and Northern Europe also have a very robust, mature offshore wind industry. So they're taking advantage of all of the specialized vessels. Port investments were paid off in previous projects, and they're really starting to see the benefits of that now.
Okay. So what's the biggest challenge you see in getting offshore wind to like North Carolina and South Carolina?
Right now, we're in the U.S. We're still fighting the cost. We're in kind of a chicken and egg scenario right now of we don't have the infrastructure. So and by the infrastructure, I mean we don't have U.S. Jones Act compliant installation vessels, and so the question is who's going to invest in that? And then on the flip that goes along with that, we also need investments in our port facilities. So when you look at the cost of a project, Vineyard Wind is going to spend, I think, somewhere between 1.5 and $2 billion on their project. That's a huge number. I don't know what the latest Dominion number is, but the full build out of that area is in excess of $4 billion. So it's huge amounts of money. But when you put into context of who's investing in the vessels and who's investing in the ports, those people aren't spending that kind of money. You can't pay for that improvement off of one project, and you need to have a long-term stable pipeline of projects that you can depend on in order to pay for that infrastructure. And so the big question is how are people going to invest if they don't have the certainty in the industry? So what we're seeing now is you're seeing states trying to come out with procurement glide paths that are long into the future. And so we started with kind of the demonstration projects, 30 megawatts, maybe 50 megawatts. Virginia's 12 megawatts. Okay, that's a project so we can get our feet wet and we can understand what's going on. But there's no way that you can pay $200 to $400 million for a port facility or $300 to $500 million for a vessel off of that project. Then you get Massachusetts coming along, and they did a fantastic job with an 800 megawatt and 1600 megawatt solicitation. So you're starting to be able to pay for that infrastructure, but still not in one project. And so now you've got states like New York and New Jersey who have announced 9,000 megawatt commitments and 7,500 megawatt commitments. And they're starting to plot out and make public which years they're going to procure that energy. And so now you're being able to start having a reliable pipeline of when projects are going to happen so that people can invest in their infrastructure and see a return on their investment. I guess that wasn't a Carolina specific answer, but I think you can recreate the answer moving south.
So, hi, Brent. Building on some of the things that Cynthia was asking about there, specifically with regard to the port support. Obviously, Charleston is a much larger port and harbor than we have in New Bern or Wilmington. And then you look at, say, Norfolk, which is huge compared to us. Do you think that we would have the port capacity here in North Carolina to be able to support what we're looking at for potential offshore wind projects, or would it have to be based out of either Virginia or South Carolina?
I do think that that North Carolina has a compelling argument. One of the things that we look at, because the day rate of the vessel is so high, the location of the port is a little bit different from traditional commerce. So in traditional commerce, you want the port to be as far upriver as possible to move goods by water, which is the cheapest way, for as long as possible. So you see something like Wilmington that's quite far up the Cape Fear River. But if you look at something like the New Bern or Beaufort, those facilities, they're very close to the ocean, so it's very easy for a vessel to get in and out of there. It makes the sailing rates, the sailing times much lower, and makes the whole process much more efficient. That said, I don't think the facilities in their current condition can support the type of loads that we need, especially for monopiles and the turbines. Those are the heaviest loads. So I think there's going to be some investment needed to be able to handle that weight. But the remaining kind of the rest of the characteristics of the port, the location, the unrestricted air draft, I think it's a compelling argument.
Okay. Awesome, thank you. One more follow-up question, more out of curiosity than anything else. You had mentioned Bushy Park with the infrastructure construction going on there in Charleston. Is that the part that's on the weapons station there? Or is that?
Yes, it's just north of the weapons station.
Gotcha.
Yes, just north.
And are you seeing a lot of collaboration with DoD sites or facilities where they're sort of interested in helping out with these things? I know they have to have sign off, obviously, for offshore, like they have in Virginia. But are you seeing any sort of collaboration there with these bases?
All of the coordination with the military from the developer side is through the DoD Geospatial Clearinghouse, and they are very active. We had a really actually quite strong. I was working on Santee Cooper's project back in kind of the 2009 to 2011, 2012 timeframe. And that the Geospatial Clearinghouse was pivoting at that point from being an onshore agency to taking an offshore role as well. But they were very active and they're very supportive. My personal experience with that agency is that they're trying to help these projects work. The other thing is that there's a vision within the military of these projects are happening all over the world, and the military also needs to learn how to operate around them. And so whether that's an issue of small patrol boats navigating through the wind turbine, or if it's radar interference from surface vessels, or whatever that potential impact may be, we're seeing a growing desire from the military to experience that and learn how to deal with it. So that's not to say that there aren't issues, and there are some mitigations that are needed, but it's been a very positive working relationship.
Awesome, thank you so much.
Hey Brent, this is Brian Drossman. I've got a couple questions about foundations. First, going back to that fully floating foundation on, I think it was a French project that you mentioned, where
Yes.
the tugs can just pull it right out to location. Does it remain a floating turbine in commissioning, or it then gets secured to some piling underground? How did that work? I wouldn't quite understand it.
Yeah, that's a great question. In this case, the one that I showed ultimately becomes a bottom fixed foundation, and so it's brought out. It's hollow when it's brought out. To lower it into place, it is initially filled with water, slowly to ballast it down to the seafloor, and then once it is in, here we go. Once it's in position, the water is replaced with ballast, so either a sand or gravel, and it's purely self-weight that holds it into position on the seafloor.
Okay.
One thing I did not cover at all is there is a large movement of the industry to move into fully floating turbines, and so that's not really happening in the Southeast because we don't need it, to be quite honest. Southeast has a huge amount of shallow water resource, so the outer continental shelf extends miles and miles offshore before we get to 200 feet deep, and so it's very economical to build traditional bottom fixed foundations here. But there are other areas of the country, like Maine, California, and Hawaii, that have very deep water, so 600 to 1,000 feet deep, where you just can't build these kind of foundations economically, and they are looking at fully floating foundations. We just don't need it here, not yet.
Okay, cool. And I had a second question too. The monopile rolled rings, where you were saying they're looking at getting some capacity to manufacture those here in the United States. Are there other industries that would have a desire for using some of that machine capacity, like so these suppliers can diversify to other things other than this specific type of foundation on a wind turbine? I'm thinking like grain silos or something. Like, do you know anything like that?
We do see for kind of the very large tunnel projects as a need for a lot of the large diameter steel caissons. So like the Gateway Tunnel in New York is looking into things like this.
Okay.
The offshore wind stuff tends to be a little bit bigger and heavier and thicker, but there are some other industries that can benefit from it. Bridge industry as well.
Okay. Yeah, I was just curious about, typically when you want to invest in a new machine like that, you gotta figure out how to fully utilize the capacity. I didn't know there was enough in the wind industry alone.
And your question is very, very appropriate. And I think that's why we haven't seen people invest so far. They're really just waiting for that certainty in the market to make the investment.
Okay, cool. Thanks.
Brent, we're running up against break. Got a few more minutes. I see we have one chat question. It's from Chris Trujillo. It says, does dredge material classification play a role in the construction? If so, what's being done? What's being looked at in the material?
I'm sorry, David. I lost the first part. Does what material?
Yeah, he says, does dredge material classification play a role in the construction?
Yep, absolutely. So there's different amounts of dredging that could be required for different types of projects. Obviously, with the gravity-based foundation, like we're showing here, it is a prepared bottom. So in that case, it's generally dredge and not fill. So the ground is dredged out. Something has to be done with that. The nice thing is, because we're offshore, the material tends to be clean. So ocean disposal is generally a more appropriate path. There's obviously all of the challenges with dredge material that you get in other industries, but it is more manageable. In a perfect world, if it's the right type of material, we can actually fill the GBF with the dredge material to use as ballast. Although if it's softer material, silts, clays, kind of things, we can't use it. But that also brings up another interesting issue. Along with the dredge material and preparing the bottom, is noise is actually a really big issue. Pile driving noise is quite significant. The monopiles can actually be heard by marine mammals almost 50 miles away. So that's why they have the observer boats on site. They also are experimenting with bubble curtains to dampen the amount of sound energy that's transferred through the water. So you get a trade-off there of what's the net less impactful construction method? Is it is it the noise in the water column, or is it impacts to the bottom?
How about one more question?
Do we have one more? I'm sorry. I know I keep asking.
No,
But
sorry,
my one last one is I want to follow up with what Brian was saying, because I feel like economic development of these port cities is one of the big drivers for offshore wind. And I was trying to think through the Jones Act, how that seems kind of in contradiction to that economic development. And I more of your opinion on the Jones Act, because it seems very curious that, again, economic development of port cities is so important. And then on the flip side, we have the Jones Act.
Yep, and someone who has more of a legal background than I could probably speak more eloquently to the Jones Act. But the main purpose of that act is to maintain U.S. competitiveness in the maritime industry, making sure that it's not all lost to foreign vessels. And part of that is guarantees or tries to ensure that U.S. ports will be used. So we do see, there's the foreign vessels that worked on the Block Island wind farm and that has worked on coastal Virginia offshore wind. But when you have a port like Virginia Ports Authority that is 20 miles away from the Dominion project versus using Halifax, which is, I don't know what the distance is, but that's got to be about 1,200 miles or so. It really, you can get away with it for a demonstration project. But for utility scale projects, you're going to have to be local. The economics just won't work out.
Brent, as always, excellent. So for those of you that enjoyed the presentation, you can unmute your video, give Brent a 2 thumbs up. Thank you, sir. Appreciate it very much.
Thank you for having me.
Yeah, you're welcome to stay with us for the rest of the day. We're going to move on. If not, back to work offshore, sir.
Thank you. Everyone have a great day.